Hi, in this video we present a work titled Context Conditional Adaptation for Recognizing Unseen Classes in Unseen Domains. Here we aim to tackle the challenging problem of zero-shot domain generalization, where during training we have access to images that belong to a set of seen classes and seen domains. For example, during training our model will see images of giraffe and horse from real and sketch domain. On the other hand, at test time, our model is expected to recognize images from novel classes and domains that have not been seen during training, for example, recognizing camel from clip art or painting domain. In addition to images, we have access to semantic embeddings that capture common class-specific characteristics or concepts that are shared among seen and unseen classes, for example, the length of neck, legs, or the presence of spots, as shown. Our goal is to recognize unseen classes in unseen domains, which implies the set of seen and unseen classes and domains during training and testing, respectively, is disjoint. Our approach is based on generating features which jointly fuse domain-invariant semantic information and domain-specific information to enable generalization to unseen classes and domains at test time. We achieve this by using context conditional adaptive batch normalization in our generative model. Now we look at the architecture of our model. Our method consists of three stages as shown. In stage 1, we start by extracting features that capture both domain-invariant and domain-specific characteristics from images. Next, we train our generative model, which is equipped with context-conditional adaptive batch normalization layer. Finally, in stage 3, we train our recognition classifier C and perform inference at test time. We will now take a closer look at each of the modules individually. We start by stage 1. Since both class-level semantic information as well as domain-specific characteristics are important for generalization to unseen domains, we train a visual encoder that can extract such features from multi-domain images input to our model. We employ a loss LR as shown for this purpose. The regularizer RF in our loss function allows us to regulate the amount of domain-invariant or domain-specific information in features F required for better generalization. Next, we train a generator G which uses context conditional batch norm layers. Specifically, we condition the batch norm parameters on the context vector as shown in the figure. The context vector is a concatenation of class-specific semantic representation and domain-specific representation for each of the source domains. We use class-level word-to-vec embeddings as semantic representations. On the other hand, the domain embeddings for each of the source domains, shown by matrices E in the figure, are learned end-to-end with the generative model. The context conditional batch norm layers enables us to instill both semantic and domain level context in output features. Finally, in stage 3, we freeze our generative model and generate visual features for unseen classes in different domains. This is achieved using the mix-up technique to interpolate source domain embeddings that were learned in stage 2, and these are concatenated with unseen class word-to-vec representations to generate multi-domain visual features. This allows us to train a classifier C on the generated features that can handle both domain and semantic shift at test time. We show the performance of our model for ZSL-DG task on DomainNet dataset. We clearly observe that our model outperforms both generative and non-generative baselines as well as previous state-of-art methods for the task of zero-shot domain generalization. In order to further analyze the usefulness of fusing both semantic and domain context, we show the TSNE visualization of multi-domain image features synthesized by our model. It can be seen that the model can better retain domain-specific variances associated with the 5 source domains within a specific class cluster when both semantic and domain embeddings are used for conditioning the batch norm parameters. Furthermore, analysis on the different potential ways to fuse semantic and domain-specific information shows that fusing information via conditioning batch norm parameters on both semantic and domain representations enables best generalization performance. In order to analyze the appropriate regularizer RF, which allows the right balance of semantic and domain-specific information in features extracted in stage 1, we test with different techniques such as Q-mix, rotation regularization, and different degrees of domain classifier-based regularization. We notice that rotation regularization gives us best generalization performance. Thank you for your time and interest in our work.